The topic is Earth's oceans during the last ice age.
Mhm.
And Jerry is a born and bred New Yorker who went to Bronx Science. And then a few years after me, went to Columbia, got his bachelor's, master's, and doctorate. After his doctorate, he went to Woods Hole and spent 10 years at Woods Hole. Returning to Columbia in 2008, he's now a full professor and chair of the Department of Earth and Environmental Sciences and a senior member of the Geochemistry Division at Lamont. He has a cruise scheduled for later this year. At that point, he will have spent 1 year of his life at sea. He's received 3 Best Teacher Awards for undergraduate and graduate instruction and a mentoring award from Lamont. He's received the Dansgaard Award for paleoclimatology from the American Geophysical Union and was selected as a Union Fellow in this past year. I think I saw him briefly in New Orleans. He's worked with many postdocs, PhD students, master students, undergraduate and high school students. And one of the nice things about his research group is that it's very inclusive. Unlike most of Lamont, there's very few white men, a lot of other people. So turning to our topic for today, we live on a very dynamic planet. The Earth's been around about 4.6 billion years. And no, Renee, I wasn't there at the start. But many times it's been covered with snow and ice. During these ice ages, the level of the sea has dropped, and at other times, interglacial periods, the sea level has been much higher than it is in the past. We can reconstruct these changes using what we call proxies, pieces of evidence to reflect the patterns we're interested in. Some of these are chemical isotopes like oxygen 18, carbon 13. We can also use important molecules like CO2 and methane and N2O, microfossils and other remnants of past life, the amount of energy coming from the sun. Many of these are recorded in deep sea drilling cores, and they can be used to create mathematical models. So here's one image which represents what the North America may have looked like during the last ice age.
Mm.
And in this image, this line represents the southern extent of the glacial ice, which in the New York area was anywhere from 1,000 to 3,000 feet thick.
Mm-hmm.
And because sea level was so much lower, the edge of the continent was probably out here.
Mm.
And then in an interglacial period when sea level was higher, areas which are now land were covered with the ocean. So the sea coast was in this red line. This has also happened, of course, in other parts of the world. In Southeast Asia, we have the Sunda Current, which flows past Borneo and Timor and places like that. And when sea level was lower, parts of what are now the Indian and Pacific Oceans were dry land.
Mm.
So the currents could not flow through. This had impacts on the climate. Some of the microfossils that we use include, everybody together, Coccolithophoridae.
Oh, of course.
We're wondering how I was going to get it in today. And here we have forams, which are calcareous microfossils, and radiolaria, which are siliceous microfossils. So the distribution of vegetation changes. We can also use that kind of evidence. And when vegetation is different, this has an impact on the albedo, the amount of energy reflected back into space,
Mm.
which will affect global atmospheric circulation and weather patterns. And the surface currents are changed. So the North Atlantic Drift and Norwegian currents, which bring warm weather to Western Europe, are altered. And changes in currents can also affect the water masses, such as North Atlantic deep water, deep sea thermal haline circulation. We also can tell what's going on in the past by using what we call IRD, ice rafted debris.
Mm.
Here we have an image of grains of terrestrial minerals like quartz. And if you look closely, you'll see some forams in here, like this one.
Mm. Mm.
And for those of you who want to go deeper, I've put a link into one of the most common mathematical models used for studying water movements. And it can simulate water isotopes, particularly deuterium and oxygen 18. And Jerry will talk more about his work. So in some of the model runs, they use a period called the last glacial maximum, which was roughly from 23,000 to 19,000 years ago. And the late Holocene, roughly the last 4,000 years, which we call the pre-industrial period. And looking at carbon dioxide, methane, and N2O concentrations. So from this, we can reconstruct changes in sea level. So I think we're ready to learn more from Jerry. Jerry's given 2 previous talks. And in 2016, I had a high school student who came for the first time to a college program. And she's now a environmental science major at McGill. So perhaps some of you who are here for the first time and still in high school will have me talking about what you do in a few years. So with that, let me end my screen share and go down here and find Jerry and make him the co-host. There we are. Jerry, I think you're co-host now, so you can.
Okay. Thank you very much for that introduction, and thanks everyone for being here. I don't know if Mike has mentioned this, but the presentation that I'm going to give today was originally part of a seminar series, a seminar course for PhD students at Lamont Doherty Earth Observatory. And it was a collaborative effort among several of us faculty members to explore oceans of other worlds and oceans of other times. The other worlds are satellites of moons of planets in our solar system. The other times are the distant past on Earth. And I mostly organized the Oceans of the Past section. And I gave this presentation on the ocean of the last glacial maximum. And in a way, it was the least interesting of all the seminars, because you can imagine it's quite mind-bending and fanciful to think about oceans on a moon that orbits Saturn, or how the ocean on Earth might have been tens of millions of years ago. the Ice Age Earth was very different, and 20,000 years ago is a relatively recent time in Earth's geologic past. So it happens that we probably know the most about this time, even though the ocean might be the least different from today. Now, it was very helpful for me to hear who you all are and where you are. I enjoyed hearing about the places, and I'm impressed with the educational credentials and with the student interest. And I should mention that Jean happens to be an award-winning member of Lamont Doherty Earth Observatory. So this is quite an impressive audience, but it's not the same audience as originally for this presentation, right? That was PhD students. So I took the following approach. I have all the same figures and slides. I didn't, if you will, dumb down any of the presentation material, but I'm not going to do an equally deep dive into the technical details. I'll try to touch upon things, and maybe we'll talk more about how it is we think we know about these times in the past. But because I know there's a danger that I'll slip into jargon or I'll make assumptions about things that you may know when you don't, please feel free to stop me and say, wait, what does that term mean, or what were you just talking about? Or you can put things in the chat. I'll try to monitor, but Mike, can I impose on you to help me keep?
Yeah, I'll watch the chat.
Yeah, if a question comes up, I'm very happy to stop. I've got a number of slides. When I presented this at Lamont, it ran on the order of 55 minutes. So it's kind of what I have in mind, but I am not going to go in as much detail, and I'm happy to address the bigger picture questions if any of you have them. Okay, with that preamble, I will try to share my screen.
We've got you.
Yeah, is that working?
It's working.
Great, good. I may minimize this so I can see what I'm talking about. I'm going to be talking about the ocean on Earth during the last ice age. And as Mike mentioned, that focus is going to be on a time that we think of as the last glacial maximum. It's the culmination of a glaciation that maybe developed over tens of thousands of years. You can even think about it as 100,000 years from the previous warm interglacial interval. But I'm mostly going to focus on the most extreme conditions. And the way we know about this, in large part, is through seagoing expeditions that acquire sediments from the bottom of the ocean. There are a range of ships that do this. There is one large international drilling program that uses technology adapted from the oil patch, but is not at all interested in looking for oil or natural gas. It's interested in drilling through a mile or so of ocean into the seafloor. And on that ship, a range of activities involve bringing up the cores, preparing them, splitting them, making initial evaluations, and then shipping them back to repositories around the world, including at times the Lamont Doherty Earth Observatory, for future study by scientists from all over the world.
Jerry, if I could pop in for a moment, just want to let the high school students know, when you get to college, there are opportunities for college undergraduates to sail aboard the Geordie's Resolution.
Quite
So
right.
if you don't find out anything about it, send an email to me and I'll link you with those programs. So you don't have to be a doctor, PhD, to sail on the Georgia's resolution. Many of the teachers, there's also opportunities for teachers at sea.
That's
Thanks, Jerry.
Yeah, that's a good point. Thank you, Mike. Now, in our group, we study the geochemistry of a number of substances, but we focus a lot on the sediment from the bottom of the ocean. We look at almost every aspect, almost every constituent, from the finest of clay particles to the microfossils that Mike was describing, to coarse debris that might have been carried by icebergs. In a way, you might say that I spend my career immersed in mud. And when I first crossed the equator, I was literally immersed in that mud. Where once these records are compiled from different places around the world, some of the evidence within them, some of the so-called proxy evidence, reveals patterns of change on the Earth that are systematic and important. And in this case, I'm going to talk some more about the proxy of oxygen isotopes. I'm going to start by showing this demonstration of a record combined from the oxygen isotope measurements in the shells of microfossil organisms that lived on the bottom of the oceans from around the world at different times in the past. And they reveal an evolution of Earth's climate from these warm intervals that are circled in red in the past, quite warm intervals, and the relatively warm interval that Mike described as the late Holocene. That's the pre-industrial, when our societies have evolved, when agriculture has flourished. The world that we know that we may be changing since the industrial age, but it was already a warm interval. And I'm going to talk about this cold interval. On this plot, values of oxygen isotope ratios that fall to the left, the high values, if you look up here on the top scale, it goes from 0 to 5. These higher values indicate cold. And I'm going to take a little detour to explain why we think we know that. But the point I'm making here is that I'm now going to be talking about the ocean in one of the coldest times within the Cenozoic, within the last 60 or 70 million years. I have to do a quick introduction of oxygen isotopes. If we were together in a room, I might ask for a show of hands to see who's got what level of familiarity with oxygen isotopes. But I'll just summarize quickly that oxygen comes in 3 flavors, and what makes oxygen oxygen is that it has 8 protons in the nucleus of each oxygen atom. There are also 8 electrons, so an oxygen atom is electrically balanced. But it turns out that there can be a different number of neutrons without a charge, but with a mass in the nucleus of an oxygen atom. And most oxygen atoms have 8 neutrons, and so their atomic mass is 16, oxygen 16. A tiny, tiny fraction of oxygen atoms have 1 extra neutron, and they're oxygen 17. And about 1 out of every 500 oxygen atoms has 10 neutrons, and therefore has a mass of 18. And all of these are stable. They all last as long as oxygen lasts. All of them are oxygen. They're in the rooms that each of us are sitting. They're part of the 20% of oxygen in our atmosphere. We breathe them in, we breathe them out as part of the CO2 that our bodies produce. They chemically are identical. They behave as oxygen, but physically they are different. They have different masses. And that becomes important in how they play out in the natural system and in how we can learn things from their redistribution. I have to introduce a form of describing the relationship of different oxygen isotopes. For today, I'm not going to talk about oxygen 17 at all. I'm going to talk about oxygen 18 and oxygen 16. Everything that I say about 18 applies to 17, but doubly so for 18 because of the mass difference of 2. Geochemists define something as the delta notation that takes this form. In this case, the rare isotope, O18, over the abundant isotope, O16, and put it in this format. The delta O18 is this ratio in some sample, a drop of water, a piece of shell, a tree, anything. We subtract some arbitrarily defined standard and then make a ratio over the standard so that if there is more O18 in the sample, this term becomes positive. If there's more O18 in the standard, this term becomes negative. And if they are exactly the same, this term becomes 0. And then we multiply that by 1,000 just because there are relatively small differences, and we can report them in the so-called per mil format, which is equivalent to percent, except it's parts per 1,000. And this is another way of saying what I just said. So I'm going to be talking about delta O18, but you can think of it as that ratio in some sample compared to the ratio in an arbitrary standard. And I think I've made these same points. And here's an important point. Oxygen is oxygen, but O16 and O18 behave differently. A water molecule that is H2O16 behaves in a slightly different way from one that is H2O18. Has a different melting point, a different boiling point, a different density, a different maximum density, a different vapor pressure, which is crucial because that means that these two forms of water don't evaporate and precipitate in the same way. The light molecule is more likely to go into a vapor phase. It's more likely to evaporate. So we'll be thinking about what happens at the ocean surface. There is always some evaporation, and it's preferentially the light isotope. But then once in water vapor or in the air, the heavy isotope will preferentially rain out. And the temperature of the system controls the amount of that separation. So we can imagine, or we can consider all the water on Earth. I defined it here as seawater, but we can define it as all the water on Earth. The delta O18 is predominantly influenced by the hydrologic cycle, the evaporation of the light isotope, the precipitation of the heavy isotope. This is the single dominant control on delta O18 in water in all forms. And through the Earth system, there are complex interactions of water molecules moving from the ocean to the atmosphere, to rivers, to ice. And it could be valid to spend weeks discussing these interactions, but for today, we are going to consider a far simpler, but very useful fiction. And that is this, that all evaporation happens in the tropics. And then air parcels move to cooler regions through middle latitudes and toward the poles. And as they cool, they can't hold as much water. And so they rain out, they condense and rain out some of that water, and eventually they snow out. This is not what happens. This is a fiction. The system is far more complex than this, but it turns out that this useful fiction captures the most important aspects of the distribution of oxygen isotopes on Earth. The oxygen isotopes in the tropical ocean become more positive. They become more enriched in O18 because it's H2O16 that's leaving. And all along the path, preferentially, the O18 rains out, H2O18. So all fresh water on Earth is isotopically negative, and all ice is very isotopically negative. Here's a more rigorous image. This captures the Rayleigh distillation of a parcel of air that contains water vapor. And I could and often do spend 20 minutes going through this, but I'm going to spare you all that. I do want to make this point. The starting point of this whole figure, this whole trajectory, is the upper left-hand corner. That is at about 20 degrees C, that's this column, and at 0 delta O18. Oh, I should have mentioned this. The arbitrarily chosen standard for water is the standard mean ocean water. It's just the delta O18 of a bucket of water from the deep Pacific. So we make the assumption here that it has a delta O18 of 0 at the starting point. And then the green line is the atmosphere, the water vapor in the atmosphere that has evaporated from this surface ocean.
Mm-hmm.
And it's negative. And that's because it has less O18 than the ocean. It's the H2O16 preferentially evaporated. Now this parcel of air, that's what the green line is, it's the vapor, it cools. And in reality, that cooling is a very complex process of trajectory and such, but we can think about the simple fiction and say it's just moving toward the poles. It cools and it can't hold as much water. So it releases some condensation, which has more O18 generally than the cloud itself, but less than the ocean because the cloud started isotopically negative.
Mm-hmm.
And then that drives the parcel of air toward even lower and lower delta O18. So as that cloud cools, the water vapor in it that's remaining in it becomes more and more negative, and the precipitation follows it, so that by the time it snows on Earth, it's quite isotopically negative. There's another way to capture that same sort of process, although not imagining that it's moving toward the poles, but moving toward higher elevation or overland. There's a certain amount of delta O18 in the vapor. What rains out is less negative than the cloud. It makes the cloud more negative. What rains out is less negative than the cloud. It makes the cloud more negative. And by the time it snows, the precipitation is very isotopically negative.
Mm.
If we can come back to this. I've come up with another analogy that has nothing to do with oxygen isotopes, but I'll hold on to that for a while. This is the net result of those processes. on Earth. The mean annual air temperature and the delta O18 of precipitation are strongly, strongly related. The colder it gets, and we could have looked at the precipitation that would fall today in each of our locations. The colder it gets, the more negative the delta O18. We can also see that play out not in terms of temperature, in this case, in terms of ocean salinity, the sea surface salinity. These red and yellow patches are more saline portions of the ocean. And there are important oceanographic reasons for these distributions, but I'll draw your eye to a couple of broad features. One is that in the subtropics, the water is the saltiest, and then special places like the Mediterranean. And in the poles, the water is the freshest. That fits the useful fiction in the following way. The precipitation is happening in these lower latitude areas, and I mean the evaporation, excuse me, and the precipitation is falling out at higher latitudes. So that makes the ocean saltier in the subtropics and fresher toward the poles. And if we were all together in a room, I might have everyone break into groups and brainstorm about how the oxygen isotopes should look. But we won't do that. I'll just show you how the oxygen isotopes look. The delta O18 is higher wherever the salinity is higher, including here in the Mediterranean. And the delta O18 is lower where the ocean is fresher. It's not because there's something magic about the amount of salt. It's because the same processes drive both observations. Evaporation and precipitation control the salinity of the ocean, and they control the delta O18. So now we're going to turn to calcium carbonate, because water is fascinating, but water doesn't tend to stay in one place in geologically relevant timescales. There certainly are ice sheets on Earth, and they're very valuable archives of oxygen isotopes in the past. But far more of the Earth is not covered with ice, and ice comes and goes geologically. So we turn to something else, and that's the calcium carbonate mineral that so many marine organisms use for their shells and their skeletons. The oxygen isotopes in calcium carbonate also have many complicated interactions. But here again, I'm going to simplify this with an approximation that probably accounts for 98% of the variability. Remember, there was only one influence on delta O18 in water. That was the hydrologic cycle. The primary influences on delta O18 and calcium carbonate are two. One is whatever the water delta O18 that's driven by this hydrologic cycle, whatever that is, that's the starting point. An organism that makes a shell in the ocean is using some of the oxygen to go into its calcium carbonate, and it starts with a delta O18. But it doesn't end up being exactly the same delta O18. The shell makes a calcium carbonate that has a different delta O18 from the surrounding seawater, and it's different as a function of temperature. So these two influences dominate the delta O18 and calcium carbonate. That means that oxygen isotopes in all marine carbonates reflect the influence of temperature. That's this second effect. And then salinity. If you remember, evaporation and precipitation also affect salinity. And we can think about global salinity being driven by how much continental ice there is in the world, because ice is the removal of water from the ocean, that's essentially fresh water, and it leaves the ocean with less water, but the same amount of salt. I'm looking at the chat, so hang on a second. As you go up in latitude, there is less O18. That's quite right. It's the delta O18 becomes more negative. There's everywhere O18 and O16, but the separation of the two, the technical term is fractionation. That fractionation drives a change so that precipitation at higher latitudes, colder temperatures, has less O18. It has a more negative delta O18. When I come back to calcium carbonate, there are these two influences. And this is just another way of saying the same thing. And you can see that the surface ocean can have values that are very near zero. Rivers in the mid latitudes, I think near New York, the delta O18 might be -10. If you go to higher latitudes, it might be -20. The Greenland ice sheet is -35. Antarctica is -40 or -50. And as I mentioned, because that continental ice always has a very negative delta O18, if there's lots of ice in the world, it leaves the ocean with more O18. The ocean becomes more positive when there's more and more negative delta O18 locked up in ice on land. So we sometimes refer to an ice volume equivalent. And then here's just some evidence to show that I'm not just waving my arms about the influence of temperature. There's a very strong relationship of the water temperature and the delta O18, such that 1 part per thousand, 1 per mil change is equivalent to 4 or 5 degrees C. And this is remarkable. This relationship is remarkable because it shows up in laboratory culturing experiments where the temperature is controlled. It shows up here in the open ocean where the temperature is not controlled but is measured. It shows up in organic precipitation experiments. And excuse me, this is just arbitrarily plotted in the opposite direction, but the meaning is exactly the same. So that all of these studies, whether they are from inorganic precipitation, from the culture of living organisms in controlled laboratory situations, or observations in the modern ocean, all of these slopes are very similar, and that allows the construction of robust equations for what the temperature is given a certain delta O18. And then this is just to hammer home the point that salinity and delta O18 are related, not because they're related intrinsically, but because the process that drives changes in each is shared. But it turns out that because the delta O18 of precipitation is different at every latitude, there's no simple single slope of this relationship. This is a relationship that we can see with our eye, but it changes from location to location and largely as a function of latitude. So we have to be careful about quantifying salinity, although we can more easily quantify temperature. Okay, then I come back to this, and I think that ends my tangent. But now we return to this idea that you can look at the variations of delta O18 through time. At the beginning of the talk, I was showing you that over tens of millions of years, we think the delta O18 in bottom-dwelling benthic organisms has changed. And this is a flipped over plot of the last 1.8 million years, with time running from your right to your left. And the delta O18 axis has been flipped so that high values are low, and high values are at the bottom, low values are at the top. The black and white bars along the bottom are the measures of the polarity of the Earth's magnetic field, and documents when it has reversed. That's not so relevant to climate, but it tells us a little bit about the time scale here. And what you can see is that these oxygen isotope ratios have varied up and down. They have generally, over tens of millions of years, been evolving to higher and higher values. But we can see here, as we blow up the last couple of million years, there are multiple oscillations that we now know to be ice age cycles. And here is the last warm interglacial. That's the so-called marine isotope stage 5. And then here, 20,000 years ago, is the last glacial maximum, one of the most extreme glaciations that the Earth has experienced in hundreds of millions of years. And then we're living here near time zero. And of course, we could have a whole talk about climate change during this interval, but today's focus is on this cold interval here. We can see that the amplitude of this change from the last interglacial to the glaciation that we call last glacial maximum, and then back to our more modern conditions, the delta O18 change is on the order of 2 parts per thousand, 2 per mil. That may sound like a small amount, but it's one that we can measure readily by mass spectrometers, and it has very large climatic implications. So now with that tangent, I'm going to step through the things that we know about the last glaciation and the Earth's ocean during that time. We think we know that the area was smaller, that the volume was less, that the average depth was less, and the amount of global ice was more than double what it is today. About 5% of all the water at the surface of the Earth was locked up in ice. And it's not quite 2% today. The temperature of the ocean was colder from top to bottom. The salinity was higher, and therefore the density of the ocean, it was colder and saltier and denser. There was greater carbon storage, which is very important because the ocean is the dominant control on how much carbon there is in the atmosphere in the form of CO2. There was greater carbon storage in the ocean that left less for the atmosphere. So the greenhouse gas influence on Earth's climate was diminished, and that's a big part of why an ice age was colder. There were lower oxygen levels in the deep ocean, and that's entirely a function or related to carbon storage, because the amount of respiration of biological activity on the microbial level that utilizes that oxygen drives the carbon storage in the deep ocean. And part of why those two things were true about carbon and oxygen is that the ocean was more stratified. deep ocean was denser and the surface ocean was not as dense. The carbon-14 ratio suggests that the water was older. And by older, as oceanographers, we mean the water had spent more time since it had last seen the atmosphere. Nutrients that provide opportunity for biological activity were trapped deeper in the ocean. And there was a greater proportion of deep water formed near Antarctica than today, where about half of the water that fills the world's oceans comes from the northern biologically productive ocean. Some regions seem to be more productive, others not so much. Okay, here is part of evidence that 5% of all the water on Earth was locked up in ice. That comes from precisely dated records, typically of corals, but in some cases of other shoreline or near shore deposits. And so the precise dating is here along the bottom. Time moves from your left to your right. And accurate representation of the depth compared to the modern sea level. And you can see that for the last 6,000 or 7,000 years, the sea level has been very near what it is today. It's currently rising. The sea level is rising in the last century, but it's rising on the scale of millimeters to centimeters. That may have a big effect on our societies, especially those that are near sea level, but it pales in comparison to this more than 100-meter change from 20,000 years ago. It's actually more than 120 meters. And that amount of water that had been locked up in ice was released and led to the sea level rise. But at this time, about 200 meters of equivalent seawater, 200 meters of the ocean were locked in ice. A little more than 120 change, and there's something like 70 meters worth of ocean locked in ice today. That may not have had a large effect out in the middle of the oceans, but it had a big effect, as Mike alluded to, here in the maritime continent of Indonesia, here in the Bering Strait. There was a land bridge across here between North America and Greenland. Then places like Santa Barbara Basin or Cariaco Basin that have very shallow connections to the ocean, very shallow so-called sills, those changes would have been more dramatic. Here's the distribution of modern temperature in a snapshot of a so-called climatology. You can see, not surprising, generally it's warmer near the equator and it's colder near the poles. There's some structure here in the Pacific. This is related to El Nino southern oscillation cycles. What we see here near Southeast Asia is the so-called West Pacific warm pool. This is the biggest pool of warm water on Earth. And here we see some reach of milder waters that move up toward the coast of Norway and along Europe. And this is what Mike was alluding to before about ocean circulation. But the big pattern is that there's warmth near the tropics and cold near the poles. And it appears from multiple records that are distributed globally and then model reconstructions that incorporate those, that it was colder everywhere, but it was especially colder at high latitudes and over the continents. A very nice recent summary by Jess Tierney and her colleagues from the University of Arizona focused on the ocean here and showed that it cooled almost everywhere, but there were special regions of relatively high latitudes where the temperature changed. The temperature change in this particular study and in most reconstructions at the highest latitude oceans are very uncertain because we have very few good records of climate change there. But in much of the global ocean, you can see this pattern. The Earth's ocean was colder by 2 to 5 degrees C. And this is the surface ocean. But we can also think about the deep ocean. Here's an image looking right down the Pacific Ocean from Alaska toward near Antarctica. And Alaska would be over here to your right. Antarctica is over here to your left. And this is the temperature of the ocean right up and down the Pacific. And you can see here, even at the equator, that the temperature is cold. This is 2-degree water at depth in the ocean. So generally speaking, Earth's ocean is cold. It's only warm in some locations near the surface. It's generally cold. And yet, we have evidence that suggests it was even colder. I'm not going to spend too much time on this, but this is a beautiful approach to capture the delta O18 of the glacial ocean by looking at pore water trapped beneath the ocean as sediments accumulate. So some of the glacial ocean, some of that water got buried with sediments as they were deposited beneath the seafloor. And then in very long cores to measure the delta O18 below the seafloor and modeling to evaluate the diffusion of that signal as the water molecules mix up and down. Those estimates converge on a delta O18 of the glacial ocean that is 1 per mil higher than it is today, 1 part per thousand. Now, if you remember, the total change evident in calcium carbonate shells was 2 per mil. So this is saying that the water signal was about half of that, 1 per mil. And the only other dominant control is temperature. The other control, the other influence of temperature indicates that something like 4 degree C change occurred. And what that means, here's the punchline down at the bottom. At all sites studied, the temperature of the deep ocean during the LGM was within 1 degree C of the freezing point of seawater. We don't think that the deep ocean froze, but it came about as close as you could get without the deep ocean freezing. So that means that both the temperature influence and salinity increased the density. So they were both higher than in the modern ocean. And this is borne out from similar approaches to looking at the salinity of those trapped waters beneath the seafloor. And the robust conclusion from these studies, I played a small role in a couple of them, but they were led by colleagues at Harvard and Caltech, and now many others have come to the same conclusion. The glacial ocean was saltier, colder, and had a delta O18 that was about 1 part per thousand higher than the modern ocean. That has some implications for carbon storage. So I'm going to turn now to carbon storage. And this is just an indication that the ocean and atmosphere are exchanging carbon in the form of CO2 all the time. Carbon is puffed out of places where water upwells from the deep ocean, and carbon dioxide sinks back into the ocean in other locations. And we think that in the pre-industrial late Holocene ocean, these inputs and outputs of carbon dioxide were approximately in balance. They're not currently in balance. We know much better today what's going on, but we also know that the system is not in balance. The ocean is busy working hard to take up carbon dioxide that human activity is putting in the atmosphere. But over long time scales, we think there's a balance. And to evaluate this, we have to turn to another isotope system, which is carbon isotopes. Just as oxygen has stable isotopes, carbon has two, carbon-12 and carbon-13. And then there is an unstable form, carbon-14. That's very useful for evaluating the passage of time. But this system of carbon-12 and carbon-13 can be utilized as delta C13, knowing that 99% of all carbon is carbon-12 and 1% is carbon-13. It turns out that physical processes aren't the dominant control here. Biological processes are. All photosynthetic activity has a strong negative fractionation. That's jargon that means that organisms that use photosynthesis, plants, in other words, they have a strong preference of carbon-12 O2 rather than carbon-13 O2. And their delta C13 is typically negative, -20 to -30 per mil, compared to an arbitrary standard. Respiration, which is essentially the opposite effect of photosynthesis, what we do and other animals to release energy, that has very little separation of isotopes. So it's really photosynthesis that drives it. And that means that all living things are isotopically negative in delta C13. And calcium carbonate precipitation preserves that signal. There's very little fractionation there. Here's an example of how carbon isotopic separation or fractionation plays out in the ocean. If you look at the solid curve here, that is a vertical section through the ocean of the amount of phosphate. That's a crucial limiting ingredient or nutrient for life. When there's no phosphate, then organisms can't produce, they can't thrive and live. So phosphate gets used up at the surface ocean by photosynthesis and by respiring organisms. And the black dots are carbon isotopes. And you can see that near the surface ocean, the ocean becomes quite positive in delta C13 because all the carbon-12, not all the carbon-12, but much of the carbon-12 is being used by organisms. So carbon-13 is low here. And then beneath the interval where light can reach, beneath the photic zone, there's only respiration, whether it's microbial or by macroorganisms, and that puts the carbon-13 back into solution in the ocean. So the carbon-13 drifts back toward lower values, but in the surface ocean where photosynthesis is using up the phosphate, it's driven to higher values. This is a demonstration that the shells of some benthic organisms, in this case, our favorite benthic foraminifera called Cibicidoides willistorfi, they are faithful recorders of the delta C13 in seawater. So we can use them to assess this following fact. I'll just cut right to the chase. During the last glacial maximum, the whole ocean had a lower delta C13. How could that be? Where did that carbon come from? Some of it came out of the atmosphere, and a large part came out of the terrestrial biosphere. There was less biogenic material on land. All of that biologic material is isotopically negative. It went into the ocean to the tune of about minus 0.4 per mil of all the carbon in the ocean, which suggests a reduction of the amount of carbon on land of something like a quarter or a third. And the implication of that, here's a more recent estimate of that. The implication is that the ocean took carbon from the atmosphere and from the terrestrial biosphere and stored it. And we know from ice cores that as the temperature has varied through time, here time is moving from your right to your left. The upper plot is temperature through multiple ice age cycles. Here's the last glacial maximum. Just as temperature varied, so did the amount of carbon dioxide in the atmosphere. In this case, this is not proxy evidence. This is actually measurements of the air that was trapped in bubbles in that ice at that time. So here at the last glacial maximum, carbon dioxide in the atmosphere was low, temperature on Earth was cold. That was part of a sequence of going up and down, but the point today is that this carbon that was missing from the atmosphere was being stored in the ocean. It was the ocean that actually controlled these variations through time. And now, in this particular plot, time is flipped the other way. So time moves from left to right. And here's the last glacial maximum. This is just essentially a blow up of that last figure, but flipped around. My apologies for that. It's showing that the last glacial maximum did indeed have these low values of CO2. And here's how carbon moves around on the Earth. There's exchange between the ocean, the atmosphere, and the terrestrial biosphere. The ocean is the largest player there. Human activity has released carbon from the solid Earth, and so that is currently a significant contributor. But the natural variation is driven over here, and it turns out that the deep ocean is the largest control. There is far more carbon in the ocean than in the atmosphere, 50 times more. Now, when I was a student in the last century, I was taught that the ocean had 60 times more carbon than the ocean. And what I teach today is that it's 50 times, and both of those numbers are right. I'll leave that to the bright minds in this audience to put the pieces together, how it can be right that I learned that there was 60 times more carbon in the ocean than the atmosphere, and I teach that there's 50 times, and both of those things are correct. But let's turn back to the glacial ocean and look at this indicator of what goes on in the deep ocean. This is a section across the Pacific Ocean in a figure from Alison Jacobel, a former student of mine who Mike also will remember. As part of her thesis, she pointed out that oxygen is flowing into the deep Pacific from the Southern Ocean. You can see it here at the bottom. These oxygen levels are higher than in the mid-depth or up above. Of course, at the surface, there's lots of oxygen because the ocean and atmosphere exchange oxygen. Now, the way that this oxygen might be used up is through respiration, that oxygen gets combined with carbon and becomes CO2. So that there's a trade-off between the amount of carbon in the ocean and the amount of oxygen in the ocean. And Allison used a technique that I won't go into detail. I don't want to bore you about this, but I'll give you the shorthand connection. It's a measurement of the amount of uranium in sediments that is controlled by how much oxygen there is in the water. When there's lots of oxygen in the water, uranium is happily soluble. But as oxygen is depleted, uranium stops being soluble and it precipitates out. You can get uranium deposition on the seafloor. And what Allison showed is that every time there was an ice age, if you look up here in the top panel, you see oxygen isotopes. Whenever they are higher values, that's an ice age. Time moves from your right to your left. Here's the last glacial maximum. And Allison showed that every time there was an ice age, there was more uranium deposition because she plotted it with higher values going down to match the delta O18. And you can see the ice core evidence of CO2 being low. CO2 in the atmosphere is low. Uranium on the seafloor is high. That suggests oxygen is low, and low oxygen means high carbon. Excuse that, it's not convoluted, but it's a long string of connections. And here in the last glacial interval, she showed that there was very strong deposition of autogenic, so-called autogenic uranium, implying low oxygen, requiring more CO2. And she showed that this applied throughout the deep Pacific Ocean. One of my current PhD students, Yusin Zhou, has shown something similar now. This is unpublished, but we are resubmitting this to the journal Geology later this month. Yusin shows that in the deep Atlantic, there also was greater deposition of uranium, implying lower oxygen, requiring greater carbon storage. So it seems that the deep ocean had more carbon. How did it get there? Why did it stay there? The way that carbon gets into the deep ocean is through productivity. Carbon is taken up by photosynthesis at the surface, then it's respired through multiple trophic levels, multiple levels of organisms using that carbon that was fixed originally by plants and algae. And you can see here around the world that there are fairly productive regions, some in the northern hemisphere, some ringing around the Southern Ocean. And there is an argument that that productivity might have been increased in the glacial time if there was an addition of a so-called micronutrient, in this case, iron. So there's the idea that iron fertilization, the fertilization by iron from the continents in the form of dust or other particles that would contain iron, that could lead to higher productivity and greater burial of carbon into the deep ocean. Evidence of another PhD student in our group, Cassandra Costa, suggests that there was no such iron fertilization in the equatorial Pacific, even though there is evidence, including from some of my colleagues at Lamont, that there was increased productivity in the Southern Ocean. Because there was not in the tropical Pacific nor in the high latitude Pacific, it doesn't appear that there was a global increase in productivity, but there might have been, in particular, in the Southern Ocean. That's, if you see these blue circles, there is an important ring of productivity that might have had the potential to put more carbon into the deep ocean. But I would say the important point is stratification. That is, carbon gets put into the deep ocean by biological productivity at the surface. Organisms die and settle down, and then the respiration of that material, often by microbial mediation, that keeps the carbon in the ocean, but keeps it in the deep ocean. And that's that process of biological activity, photosynthesis near the surface, respiration at depth, that has come to be known as the biological pump. That does put carbon in the deep ocean, and then it comes back out. Remember, I said pre-industrial, we think the ocean and atmosphere were in a balance. The reason the way it comes back is not through biology, it comes back through physics. Physical motion of this carbon-rich water in the deep, if it can get up to the surface, it puffs right back out into the atmosphere.
Yeah, upwelling.
And so the degree to which the deep ocean is physically separated from the atmosphere by a density contrast of water with less carbon near the surface, that controls how well the ocean can hold all that carbon. And here again, we can turn to carbon isotopes to give us an indication. Those carbon isotopes here, this is, you see just the tip of South Africa. So this is evidence through the Southern Ocean in the interval of time that Mike described initially today, the late Holocene. You can see that the carbon isotopes near the surface are relatively high. And then in the deep ocean today, in the Southern Ocean, they're a little bit lower. There's not much difference. You know, it's tenths of a per mil. But in the glacial ocean, if you go down in sediment cores back to the last glacial maximum, the near surface values are very similar. They are different by about the amount that the whole ocean changed. So this change from Holocene to last glacial maximum is probably due to the addition of carbon from the terrestrial biosphere. But look at what happens in the deep ocean at the last glacial maximum. Very negative values. That suggests that the biological pump pumped carbon down to the deep ocean, and then it just sat there. And it sat there, and respired and respired and respired and put that negative carbon right back into solution without mixing it back up as happens today in the Southern Ocean. So it really looks from this figure that the Southern Ocean stored more carbon at the last glacial maximum because of stratification. Here's a view, the top panel of carbon isotopes in the modern Atlantic with, to guide your eye here, the left axis is water depth, the bottom is latitude. So on the right is the high northern latitude Atlantic. On the left is the high southern latitude, and the equator is here in the middle. And the colors and the contours are carbon isotope measurements in seawater and in foraminiferal shells at different water depths. And you can see the ocean, the Atlantic Ocean today is flooded with high C13 water that has recently been at the surface and sunk to produce the North Atlantic deep water. And here at the glacial interval, there was water from the north with high C13, but much more of the deep Atlantic was flooded with low del C13 water from the Southern Ocean. Water that could even have emanated from these low C13 values. And this suggests also in the Atlantic a strong stratification between the deep ocean that was storing carbon and the shallower ocean that was not. And multiple lines of evidence, multiple types of measurement, including carbon isotopes, including the ratio of cadmium to calcium, which tends to co-vary with phosphate. So cadmium is like a paleo proxy for the phosphate measurements that we see in the modern ocean. Here's what the Atlantic looks like today, and here's what it looks like in carbon isotopes and in cadmium at the last glacial maximum, with this very expanded so-called AABW, Antarctic bottom water, that is carbon rich and sufficiently dense that it would not mix up. It would hold the carbon that the biological pump is moving there. It's also true in the case of neodymium isotopes, which have nothing to do with biological cycling, but they are just incorporated in seawater in different isotopic ratio depending on where the waters meet the continent. So all of these lines of evidence converge on a much more stratified Atlantic. Here's yet another proxy that I won't go into, but it's telling that same story. And here is that view from the Pacific based on neodymium isotopes that suggest a more stratified Pacific Ocean. Very vigorous overturning in the Holocene and much weaker in the Glacial. And summing this up, here's I think, a beautiful, if potentially confusing, conceptual image by Lynn Talley of Scripps Institute of Oceanography, showing how the waters of the ocean today mix from the surface to the deep and through each of the basins. Whereas at the glacial maximum, there was a much stronger separation of the two. This is work by Ralph Ferrari at MIT that shows a stratification where the shallow circulation went around and around, and the deep circulation dwelled much longer at depth. A last point is that radioactive carbon isotopes tell that same story. Carbon-14 moves through the ocean, and the glacial carbon-14 suggests that in each ocean, Southern Ocean, Pacific, Indian, and Atlantic, that the water was older, that there was less carbon-14, meaning the water had stayed at depth for longer and was holding that carbon. So in summary, the glacial ocean was smaller, shallower, colder, saltier, denser, more carbon rich, oxygen poor, possibly more productive, although some regions it was more productive, maybe not all. Could have been important that it was in the Southern Ocean, but clearly the glacial ocean was more stratified. Whatever carbon was pumped into the depth tended to stay there, in part because it was filled with Southern Ocean deep water, and in part because the deep waters tended to stay there longer. And therefore, the ocean was largely responsible for the lower atmospheric CO2 that contributed to the glacial conditions.
Thanks, Jerry. We have a couple of questions in the chat.
Great.
Richard wanted to know a while back, what about the spike near the equator? Richard, do you remember which spike you're talking about?
It was a line drawn from north to south latitude.
Yeah.
It's about, I mean, 7, 8 slides before you were going
No-
across. It shows how the deep ocean, was it the deep ocean? I don't know, was the carbon dioxide? It was a big spike.
Big spike. And
Yeah.
about 7.
Yeah, you were with the Pacific Ocean. You were transecting from the north to south
in the Pacific. Okay,
in the
that's-
Pacific. Yes.
That's helpful. Let me. Oh, could it have been in Allison's figure of? I'm going to take a guess that it might be this, but maybe it's this, and in which case I might have an answer. But let's confirm if this is what you're talking about. Not this.
No, that's east and west, north to south.
It was definitely north to south. Okay.
Yes.
I did it north south. This is north south.
Is that it? Yeah.
Okay. This is the main point here was the temperature of the deep ocean, but it is of course a profile from north to south of temperature right from the surface to the bottom. And I didn't explain this well, but just as an accident of where this profile is, the sea floor varies in depth. So that's what it's brownish in my view. This is the bottom of the sea. So the spike at the equator just means that there is not a seamount, but like a shallower ridge here near the equator. And then this probably is a guyot or a seamount. This might even be, we near the Aleutians, it might be an island. These are, if the profile was moved a little east or west, this bottom part would change. But the temperature field throughout the deep ocean is largely the same.
All right. I understand now. Yes.
Okay, was that the point? Was it
Yes.
about the bottom?
Yes.
Yeah.
Yeah.
'cause
It was
then-
just.
Yeah. It's this. It's just because I show this profile. If it were moved, a couple 100 kilometers one way or the other, the bottom would change. And if I took an average of all of those, the bottom would smooth out, right? But
I see.
the temperature profile would remain the same. And this, I start some of my introduction to the deep ocean with a figure like this, although I start it east to west, because this gives away the answer. The deep ocean is really cold, even though the atmosphere is relatively warm. The Earth underneath is hot in the middle. How can it be that this ocean is so cold? Here's how it can be that it's so cold. The waters that become dense enough to fill the deep ocean get their properties at the surface at the very high latitudes. They get cold here around Antarctica, and then they spill into the deep ocean, which is a bit of an aside. 20 north could well be Hawaii. That's a point.
Jerry, another question Richard had is what caused the oceans to change?
Really good question. It depends which aspect. What caused the ocean to change temperature is probably that the Earth's surface temperature started to change. And so the waters that filled the deep ocean formed in colder and colder places. The ocean's change in salinity was driven by the growth of ice on land. The ocean's change in carbon storage could have been a function of changing productivity patterns, but I happen to think it was largely driven by changing circulation patterns as areas that were proximal to ice growth experienced increased annual melting. So near ice, there's spring ice melt. So as they became fresher seasonally, that would mean less production of truly deep water, of water that was very, very dense. And so I think that the ocean changes were in a way a highly influential and highly interactive feedback to changes that were happening anyway. The ocean didn't drive the ice age cycles on its own. The ocean contributed to them. They were probably triggered by insulation changes, by the so-called orbital or Milankovitch changes of seasonal distribution of sunlight. And then I think the ocean changes, I just mentioned what I think are the proximal explanations, but what triggered that whole process is probably changes in sunlight. But then of course the ocean storing so much carbon lowered atmospheric CO2. That's an important greenhouse gas feedback. A cooler atmosphere would hold less water vapor. Water vapor is the most common greenhouse gas, so that's its own feedback. So, and then the growth of ice and the expansion of tundra, for example, the decay of the loss of forests, all of those things would increase the Earth's albedo, its reflectivity. So in the end, all of the big climate influences contributed to a colder Earth.
Thank you very much, Jerry. Do we have any other questions from participants? So that was
I'm not sure.
basically-
You might have just answered mine, but I was curious about, I'm trying to figure out how to post. Like what
Just ask it,
triggered
Gene.
past ice ages? Well, I know when I worked with Peter Schlosser, he talked about the cold glacial melt dropping into the Labrador Sea and stopping the ocean conveyor of moving our nutrients and heat and stuff around. And is that part of any of this? And wouldn't we, I saw on your ice age chart, wouldn't we be naturally going into an ice age now? if it weren't for all of this?
Those are two good questions, and I especially like the second one. Although the first one is up my oceanographic expertise, it's the answer is yes. The changes in circulation that you and Peter Schlosser would have discussed in the past, this change in the conveyor, I didn't introduce it so much as a conveyor today, but in my response to the previous question, that's what I was talking about. If areas that are at high latitude, for example, in the North Atlantic today, that's where about half of the water that fills the deep ocean gets its properties in the Labrador Sea, in the Greenland Sea, in the Norwegian Sea today. The reason that happens is that warm, salty water moves up through the Gulf Stream, through the North Atlantic Drift. It's salty water, it reaches high latitudes, and it cools. It cools and sinks as dense water to the bottom. That's today's North Atlantic deep water. If those areas at high latitudes were fresher in the past, then it would get every bit as cold, but the water wouldn't be as dense and it wouldn't sink as deep. And so that image I showed you of the glacial Atlantic, where the deep water is coming from the south, not the north, that's exactly what Peter would have been talking about, that it's a contribution to the heat transport, but I would say it might even be a more important contribution to the carbon storage in the deep ocean. If the North Atlantic waters were not as dense, they wouldn't fill the whole ocean, and they would just circulate at above that. And I still think that that's the case. Then the second beautiful question is the orbital theory of climate change suggests that northern summers are the important pacer for ice age cycles. When northern summers are particularly warm, the Earth becomes interglacial. When northern summers are particularly cool, the Earth experiences glaciations. The Earth's nearest approach to the sun, right now, it's so-called perihelion. Anyone happen to know when that is in the year?
January.
It's very early in January, that's right. So think about that. The Earth is closer to the sun in the northern winter. That means it's farther from the sun in northern summer. That means northern summers are cooler. That means Gene's question is really relevant. Shouldn't we be moving into an ice age? And according to the Milankovitch theory, the answer is yes, but we in our group and others have made a similar argument, is that the Earth's orbit is very nearly circular right now. So even though perihelion happens in January, perihelion and aphelion, the nearest approach and the farthest approach, they're not very different. The Earth's orbit is not very eccentric. It sometimes becomes eccentric over 100,000 years, but right now, we would argue the insolation isn't low enough to cause a true ice age. It might lead to a little cooling. We would say the next true ice age in a natural progression would actually be many, many thousands of years in the future. Now we add this complication. The Earth's greenhouse gas concentration in its atmosphere is far higher than any previous glacial or interglacial. So you could make the argument that both from the insolation point of view and the greenhouse gas point of view, the Earth is just not poised to go into the next ice age. I would say, in terms of insolation, not for tens of thousands of years, from the perspective of greenhouse gases, we just don't know because this is non-analogous to any glaciation that started in the past.
Jerry, thank you very much.
Thanks, Jerry.
That was basically 1 or 2 semester courses in
That was a really great.
one morning.
Yeah, well, thank you all for your patience and attention. I appreciate it.
Thank you. The next Earth Day class will be on February 19th. I didn't find a speaker for February 5th. So the next one will be February 19th. We're going to have Chris Zappa returning to talk to us about some of the impacts the climate change is having on Alaskan communities. So I hope many of you will be able to come and join us for that. I'll send information out to everybody. I'll also send out certificates of participation and let you know when we get the video posted for everyone to look at again if you wish. Okay, thank you all very much. Jerry, greatly appreciate your taking the time to share your expertise with us today.
Thank you
Hope all the
all.
plants have
Thank
been watered.
you.
Thank you all. Yes.
Thank you so much.
Okay.
Bye-bye.
Bye
Bye-bye.
all.